Okay, good. All right. So, good evening, everybody. Welcome to PH 870. Let me see. All the usual suspects are here. All right, excellent. So what we have done so far is we have covered all the mathematical preliminaries, and I think that the detail that I have covered so far is going to be enough to get us most of the way. It's good to get us well into anything, almost anything we want to do with as far as quantum algorithms and all are concerned. Of course, wherever some new information is required, as and when, I will introduce it. Okay. All right. So the first thing I want to talk about today is something called the Bloch sphere. Right. So we have finished the mathematical preliminaries, which took a little bit of while, and maybe you got tired of listening to the same things over and over again. Anyways, so what is this Bloch sphere? Well, it's a visualization of a single qubit. Okay, and now you might think that, well, how useful is it going to be to visualize a single qubit? I mean, aren't quantum computers going to be made of like thousands and thousands of qubits? And the answer is that, well, yes, they are made of thousands of qubits, but it is quite surprising how effective this simple visualization can be for many purposes. Okay, so this is a sphere, right? Obviously, and let me just move it a little bit. And what this sphere is supposed to represent, it's supposed to represent a single qubit. Okay, so a single spin 1/2 particle. Now here's the correspondence. The North Pole corresponds to the 0 state, and the South Pole corresponds to the 1 state. Okay, and you might find that correspondence to be a little bit odd, but it will make sense eventually, I hope. Okay, and the points on the surface of this sphere right, so you can have some arbitrary point on the surface of the sphere. Let's call that will correspond to an arbitrary state of your qubit. Okay, now we can write down a qubit, right, as a superposition alpha 0 plus beta 1, right? Okay, we will use a slightly different parameterization, right, which allows us to map this to the Bloch sphere. Okay, and that parameterization is the following. We can write this expression. So first of all, you know that alpha and beta, they both add up, the modulus squared adds up to 1, right? So you might think, well, one obvious kind of parameterization would be to set alpha is equal to cosine of something and beta is equal to sine of something, right? Let's say cosine theta plus sine theta, right? This is what you might think. Okay, well, you can do that, but this will not be very useful. And even if you do that, there is a relative phase, right? Because see, these can be complex numbers, right? So this is the first constraint, right? But then there are complex numbers, right? And these are real numbers, the ones that I've chosen over here, right? Cosine and sine. So in general, there can be a complex phase let me call that e to the IA, let's say, cosine theta, right? And another complex phase here, e to the IB sine theta, right? But now what I can always do is I can pull out one of these phases, right? And write this as B minus A sine theta, like this, right? And this phase we can always drop, okay? Because as I've told you before, wave function states are only defined up to a phase, right? So this is equivalent to e to the I theta psi, right? So we can write our state as cosine theta 0 plus e to the I phi sine theta. And this phi is what? This is that phase angle, right? The relative phase between the up and down states. Okay.
Sir, why did you cancel e to the I?
The reason that this parameterization is not terribly useful is because, for instance, sorry, did somebody say something? Okay.
Yes, sir. Like, why did you strike out e to the IA?
Because, like I said, now wave functions are only defined up to a phase.
Is it because they could be periodic? Is it because they could be periodic?
No, it's because if you, for instance, if you take a expectation value, right? The expectation value is not affected by a phase, no? Right?
Yeah.
Or if you take the expectation value of any operator.
So I didn't understand why we multiplied by e to the power IA and e to the power IB in the first place.
Well, because alpha and beta are in complex numbers in general, right? These are complex numbers in general, right? They are complex numbers which satisfy this this requirement, right? So the probability is the modulus squared of the complex number, right? So here I have restricted to the real line only, right? But in general, they can be complex. So there should be a complex phase, right? For any complex number. This is the amplitude. There should be a corresponding phase also, right?
Yes, sir.
This is the phase for the first one, and this is the phase for the second one, right? Then I pulled out one of these, right, and written that as the remaining part is this, right? Okay. Okay. Now, and just to clarify, leave this over here 1 second. So let's say this is psi prime. Okay. And it's equal to this, right? Then, first of all, the expectation values are going to be equal, right? Of psi and psi prime. And so this will be an equality. I'll just fix that. And secondly, the expectation value of any operator is going to be the same in both the states, right? So the phase is not going to have any physical effect in, right? Fine. And this is also something that I've like told you before, like when we talked about the Hilbert, what is the Hilbert space? Well, it's way back. I don't know where it is. I won't go back. That states are only defined up to a, not just a phase, actually a multiplication by an arbitrary complex number, because the length of the state also is not relevant. You can always normalize the state, right? It is the relative length of the components that matter, right? And those components always, the length of those components always add up to, length squares of those components always add up to 1. Okay, is this fine? Are there any other clarifications? Rohan, is this fine?
Yes, sir.
Okay, if there are any other questions, please let me know, okay? Because these seemingly small things can create problems later, okay? So we don't want that to be the case. All right. Now, so, well, I mean, what is wrong with this parameterization? Why can't we just use this cosine theta and sine theta, right? So the reason is, for instance, let me set phi is equal to what is it going to be? Phi by 2. Yeah. Let me set phi to be any. Let me not set phi. Sorry. Okay. Let me set theta to be equal to let's say pi by 2, right? Then what is phi? Phi becomes 0, right? If theta is equal to sorry. For pi by 2, it's e to the I phi, e to the I phi 1, right? Because cosine pi by 2 is 0. And similarly here, psi is going to be 0. Okay. But okay, well, let me just write down the final parameterization. And I guess the proof is in the pudding, as they say. So, and then we'll see how that corresponds to the Bloch sphere. And so this is the final expression that we need, okay? And this represents a state on the Bloch sphere, which I will again copy over here just for reference. Okay. And now theta and phi, right? What are these two angles? So theta is the angle from the vertical, right? So in spherical coordinates, you write, you have r theta phi, right? Or actually, since I'm using the curly phi, I'll stick to that. R theta phi. And in Cartesian coordinates, you have x, y, z, right? And this x, y, z is nothing to do with position, by the way, okay? Don't get confused, right? So how do you, what is the, you say r, x is equal to r sine theta cosine phi, r sine theta sine phi, and z is equal to r cosine theta, right? So this is that angle theta. And of course, in our case, r is equal to 1. Okay? Because our states are, we'll take our states to be normalized. Okay? So we are always working with the unit sphere. And we are always working with the surface of the unit sphere. Okay? We will see that points inside the unit sphere also have an interpretation, but we'll come to that later as certain kinds of states. Okay. And phi is the angle from So if you drop a vertical line from here, right, another line from here, then phi is this angle. Again, I'm using the wrong phi, curly phi, right? Okay, so all of you are familiar with this construction, right? So one would write this as the quote unquote x-axis, for instance. This would be the y-axis, this would be the z-axis, right? And so in this picture, what we have is that, so let's set theta is equal to 0. Theta is equal to 0, right? So when theta is equal to 0, you are at the north pole, right? And what is phi is equal to 0, okay? Right, now when theta is equal to, what is the range of theta now? This is the important thing. When theta is equal to pi, right, that corresponds to the south pole. When you're on the sphere, 0 is the north pole, you go all the way down, that's 180 degrees, right? So you're at the south pole. So now what is psi? Now, see, this is cosine theta by 2, and this is sine theta by 2, right? So cosine theta by 2 is pi by 2, and that is 0, right? And sine theta by 2 is sine pi by 2, that is 1. So at the south pole, this becomes equal to e to the I phi 1, right? But then at the north pole, this psi is not really well defined, right? So you know, you can just ignore it. You can just forget about it, right? It's just psi is equal to 1. All right. So these are the two, the north pole and the south pole, right? But now, what happens in between? Okay. So in between, what does the equator correspond to? The equator of the sphere corresponds to theta is equal to pi. Pi by 2, right? So theta is equal to pi by 2. This corresponds to the equator, right? So this is our equator, right? Now, and I'm drawing it like in this kind of perspective. Okay. And what is psi? Well, so it becomes cosine pi by 4, right? Pi by 4, 0, plus e to the I phi sine pi by 4, 1, right? So this becomes equal to 1 by root 2, right? 1 by root 2, 0, plus e to the I phi 1. Okay. Now, what are the yes, is there a question? Sorry, is there I don't know if somebody said something or you didn't say something, I didn't catch that. Okay. So now what is the range of phi, right? So this is the phi angle, right? And phi goes from 0 to 360, right? So if we set phi is equal to 0, right? And so theta is equal to pi by 2, this would correspond to the quote unquote x-axis, right? According to our choice of coordinates. And psi becomes root 2, 1. That's just the normalization. 0 plus 1, right? Theta is equal to pi by 2, phi is equal to pi, right? So this corresponds to the negative x-axis, right? What is psi? Psi is 1 by root 2, 0, minus 1. Okay. So all the points on the equator correspond to an equal weight superposition of the two states, right? So all the points on the equator, because the amplitude of the two coefficients is just 1 by root 2, right? There's a relative phase factor e to the I phi, which is important, which is physical, because it's a relative phase factor, not an absolute one. All right. So this is our description of the state space. This is 0. This is 1. Any point here is 0 plus e to the I phi 1. And then as you go to as you vary theta, that varies the relative amplitude of the two coefficients of alpha and beta. Okay. All right. Now let's talk about gates, and let's talk about the effect of gates on these states, and we'll see how the Bloch sphere helps us in visualizing what is going on. Okay, because now what you can do is you can view any point on the sphere as a state. Okay, and so there is a one-to-one correspondence between points on the sphere and the states of a qubit. So you can view the evolution of a qubit as the movement of a point on the surface of a ball. Okay, right? So this is my ball, let's say. Okay, and I guess this is my sphere, and any point on the surface of the sphere represents my state, and I can take any trajectory, right? And this trajectory, for instance, corresponds to psi t. This state corresponds to psi t. This state corresponds to psi t prime. And so this trajectory represents the evolution of x. Okay, so it gives us a geometric picture. And geometric pictures are always nice because, well, our brains and our intuition is inherently geometric. So now let's look at this X gate. Okay, so this is the Pauli X gate. In quantum mechanics textbooks, you will also see this written as sigma X. Okay, and it could come with or without a factor of 1/2 outside. That doesn't really matter. So what this is, it's called the NOT gate. Okay, so this is we will see that it has the same effect. So it's a quantum NOT gate. Okay, and what is the effect of this on a state, right? So the state is alpha beta, some coefficients alpha beta. What does it do? It takes the two coefficients and flips them, basically, right? So if you act on a 0 state, you get the 1 state, and if you act on the 1 state, you get a 0 state, right? And what will be the eigenstates of this? Well, the eigenstates of this, one can guess, are going to be equal weight superpositions of 0 and 1, right? So these are the eigenstates. All right, now So another gate, okay, is the Z gate. So the Z gate is called the what is it called? Well, it's just called the Z gate. Okay, and we already, well, we know what it is. This is 1 0 0 minus 1. What is the effect of the Z gate? It leaves the 0 state unchanged and it gives the 1 state minus 1. Okay. Now I hope that all of you are able to follow these manipulations. For some of you, this is all like very, very boring and very trivial. But I want to make sure that for everybody else, that nobody is getting lost. Okay. Then we have another very important gate. This is called the Hadamard gate, and we'll be using this a lot of the time. And okay, and what does the Hadamard gate do? So the Hadamard gate, if you act on 0, for instance, okay. So again, let me, for the sake of just to be very slow for those who are still trying to follow things, right? I won't keep doing this for the whole semester, don't worry. Right? So what will this give us? This will give us 1 and 1, right? So I can write this as 1 by root 2, 0 plus 1. Okay, so H acting on the 0 state gives me a equal weight superposition of 0 and 1. And H acting on the 1 state gives me an equal weight superposition, but with a negative sign for the 1 state. Okay, and we'll be using this all the time, right? So these are some things that you should like have at the back of your mind. Okay. Then the H state has another property that if you take the square of this matrix, okay, so what do you get? You can work it out, and this gives you X. Okay, so you can think of this as the square root of the NOT gate, quantum NOT gate. Okay. I don't know how useful necessarily that point of view is, but Rakshit just found something interesting. What did you find interesting, Rakshit? You said interesting in the chat, so can you tell us? Oh, class is interesting. Okay, well, thanks. I appreciate that. Okay, so apart from so what are these gates? X, Z, H, and others that we'll talk about. These are all single qubit gates, okay, because they act on 1 qubit. All right. And now the thing is that any 2 by 2 unitary matrix is a quantum gate, right? Is a quantum gate. And so this means that there is an infinite number of these single qubit gates, right? Because so there is a certain way to decompose a single qubit, okay? And I'll write that down, right? But we'll come to the proof of it later in the course, okay? So any single qubit unitary can be written in this way. And I will talk about let me just write down the expression first. And then we'll see how the Bloch sphere picture allows us to understand what is going on. So any single unit qubit unitary can be written in this way. Okay. In terms of 4 parameters, alpha, beta, gamma, and delta, which are real numbers. Now, this looks somewhat similar to if you have studied it, there is something called the Euler angle decomposition, right? Of rotations in 3 dimensions. So any rotation in 3 dimensions can be written as a product of 3 rotations: a rotation around the x-axis, a rotation around the z-axis, and then another rotation around the new z-axis, right? So this is somewhat similar in spirit to the Euler angle decomposition, right? So there are 4 angles, and what are each one of these matrices doing, right? So if you look at the effect of this first matrix, let's say, okay, and we ask how does it act on a single qubit. Well, so our qubit has this parameterization, this Bloch sphere parameterization, right? So these are the elements. So if we just multiply this, what do we get? We get e to the minus I delta by 2 cosine theta by 2, and e to the I delta by 2 e to the I phi sine theta, right? We get this. Now, again, right, I'll call this psi prime. Again, we can take a factor of e to the minus I delta by 2 out of the state, right? I can write it as cosine theta by 2 plus e to the I phi plus delta sine theta by 2, 1. Okay. Now, in terms of the Bloch sphere representation, what is going on? Theta doesn't change, right? Theta doesn't change. Phi changes, right? So phi is going from phi to phi plus delta, right? So in terms of the Bloch sphere representation, what this corresponds to, again, I will hopefully, 1 second, let me, running out of pages, I need to. Okay. And how many of you like have to leave at 6 o'clock? Is that doing if you have to leave right at 6 o'clock? Rakshit has to leave. Okay. So in terms of the Bloch sphere picture, what does this gate do? So you have a state, right? And Okay, this is your state psi. And what is the effect of this gate? Right, the effect of this gate is that it takes this state psi, right, and it rotates it about the z-axis, right, by an angle which is given by delta, right? So if I draw it like this, then if the initial state was at an angle phi, okay, then this final state, so if the initial state is at an angle phi, the final state is at an angle phi plus delta. Okay, that is the effect of this gate. Then you have this gate in the middle, right? Okay, and what is this? This you might recognize as minus sign. Okay, what is this? This, if you, I don't know if you recognize it, but this is a rotation in 2 dimensions. Okay, so if you have some xy plane, for instance, if this is xy, and if you multiply by this matrix, then what it does is it rotates your, whether, depending on the sense in which you are performing the rotation, it performs a rotation by gamma by 2, right? So so in this case, however, our notion of x and y is slightly different, right? Our x state is the north pole and our y state is the south pole, right? So this performs a rotation that is along the what would we call it? A great circle. Okay, so if we work it out, if we take this matrix and multiply it by our state, cosine theta by 2 e to the I phi sine theta by 2, right? You can work it out. Well, I'll leave this as an exercise for you. Okay, exercise, plot the result on the Bloch sphere. Okay, so any single qubit unitary can be decomposed into these 3 operations. The first is a rotation around the z-axis, then this transformation, then another rotation around the z-axis, and then multiplication by some arbitrary phase. Okay. All right. So now we will come to where quantum computing, or something non-trivial starts to happen, and that is when we work with more than one quantum state. So we have to work with multiple qubits. Okay. So the most important multiple qubit gate, well, I mean, the most important in the sense that, well, it's used most often, but of course, some people might argue that it's not necessarily the most important one anyway. It's called the CNOT gate. Okay. And the C stands for controlled. All right. Now, what is the NOT gate? The classical NOT gate does the following, right? It takes 0 to 1 and 1 to 0, right? So the quantum NOT gate should take 0 to 1 and 1 to 0, right? And which gate does this? The X gate, the poly X gate does this, right? Poly X gate swaps the two components. So now let me first draw the circuit, and then I will explain to you how the circuit is working, okay? Okay. So this is the circuit representation of a CNOT gate. All right. So there are two qubits. Let's call this A. Let's call this B. A is called the control qubit. Okay. And this dot over here, this tells us that this is the control qubit. All right. So the control qubit determines what happens to the target qubit. You can call it that, I guess. This is the target qubit. So the effect of this circuit is the following. The A qubit is unchanged, and the B qubit is changed. Where I have used this symbol, right? What is this symbol? This is called the XOR, right? So let's work it out in a few cases, and then we'll see what this means, right? So what is XOR, right? This is the classical XOR, right? So what is the truth table? If you have 0, 0, 1, 0, 0, 1, 1, 1, right? So these are your inputs. Right? And then your output is 0, 1, 1, and what does it do? It's 0. Okay. So this first one is the control, and the second one is the target. Okay. So this is A, this is B, and the third column is A XOR B. Okay. So XOR stands for exclusive OR. Exclusive OR. That means only A has to be non-zero or only B has to be non-zero, right? Now, okay, what just happened? 1 second. Now, so let's say that A is in the 0 state, right? And B is also in the 0 state. Then what is the result of this A XOR B? It's the 0 state, right? So you can think of this as the A gate, B gate, and A XOR B. Okay. So what does this tell you? This tells us the following. If the A gate, the control qubit, is in the 0 state, right? So over here, where it is 0 here and here, right? The target qubit is unchanged, right? So this is the target qubit, right? The second two columns. This is the target qubit before the operation, and this is the target qubit after the operation. So if A is 0, then the target qubit is unchanged, right? So if this is 0, the target qubit is unchanged. But if A is equal to 1, then the target qubit is flipped from 0 to 1. right? So if this is 1, the target qubit changes the state, whatever the target qubit is. Okay. So for instance, if A is equal to 1, then B is equal to 0, then A XOR B is equal to 1, right? So what is the effect of the CNOT gate? It's the following, that if A is equal to 0, leave B alone, don't do anything to it. And if A is equal to 1, then B goes to XB, right? The quantum NOT gate. Okay. Now, the thing is that the way I have described this picture, this is a very like classical description, right? Because I have not mentioned anything about superposition and so on. At this stage, you can just think of these as bits. But life becomes more interesting once you realize the following, right? That that these input states in general, these input states need not be 0 or 1, right? They can be some superposition of 0 or 1, right? So in that case, what happens? So for instance, let psi is equal to 0, and we'll take phi to be some superposition of 0 and 1. Okay, and so what is the effect of this gate? What is the output state over here? The output state is the following. In this case, well, nothing happens, right? Why? Because psi is 0. So I'll put a phi prime over here. So if psi is 0, phi prime is equal to phi, right? But if psi is equal to 1, then what happens? Phi becomes beta 0 plus alpha 1, right? Now, okay, so I hope that you understand why this is called the control NOT. This is the control qubit, the first one. And the second one is the target qubit. So the target qubit switches state, undergoes a NOT operation only if the control qubit is on, so to speak. It's in the 1 state. Okay. Now, yeah, go ahead.
Sir, in this, like the control and the target bit, like they can be interchanged and still give the same result, right? So are they interchangeable in our, like the control bit and our target, the states, both of them can be interchanged and you still get the same result, right?
No. Okay, of course not. No, of course not. Because I mean, you can just see that very straightforwardly, right? Let's say that well, okay, yeah, I suppose you're right about that. But that's only when they are in this 0-1 state. Okay.
So here actually only the coefficients are getting interchanged, right?
Actually, just let me finish my answer. 1 second. Huh? So only if they are in these eigen states, 0 and 1. In that case, switching the two states, like you said, is not going to change the result of the output. Okay, that's fine. But the thing is that they don't need to be in the 0 and 1 state. No? They can be in some arbitrary superposition. But more importantly, okay, and this is the important part, psi and phi, this full thing, right? See, this full thing together, it's an element of the Hilbert space of what? It's an element of the Hilbert space of 2 spin 1/2 particles. Right? So the Hilbert space of 2 spin 1/2 particles. So the Hilbert space of 2 qubits. What is the basis of this? Rakshit, I'll just come to your question in 1 second, okay? If you remember, this is the basis, right? This is the set of basis vectors of the Hilbert space of 2 qubits, right? How do we get this? This is a tensor product, right? And I think I've gone into the tensor product in some detail,
yes,
in my previous lectures, right? If I'm not mistaken. Right? So I have gone into this in some detail. 1 second, my internet is unstable, it's not updating. Can you see the screen updating?
No, sir.
Yeah. So okay. So I've mentioned this in some detail, right? So I won't go into this again. All right. And so these states, these are my basis states, right? Now what I have told you so far are the following, right? So the input state of my circuit, I've used the following inputs, right? I've used only these basis gates as my inputs, right? I've used either 0 and 0 or 0 and 1 or 1 and 0 and 1 1, right? These were my inputs. So what happens to 0 0? Nothing happens, right? So this is the CNOT operation. I guess I should put the arrows going downwards. Anyways, what happens to the 0 1? Nothing happens. What happens to 1 0? It becomes 1 1. What happens to 1 1? It becomes 1 0. Right? That's what the CNOT gate is doing now. Maybe should draw the lines going down like this. Arrows going down. Right? So this is what the CNOT gate is doing. If I write this in terms of coefficients, in terms of vector components, right? These are the vector components. Right? These are the vector components. So what does the CNOT gate do? The CNOT gate, it swaps these two components, right? So if I have an arbitrary state of my system, and now other than psi and phi, I don't know, let me use something chi, right? So an arbitrary state of my system is represented by 4 numbers, right? And what is the effect of the CNOT gate? The CNOT gate does not change the first 2 components, right? Because these basis vectors are unaffected. And what about the other 2? It swaps them, right? So this is the effect of the CNOT gate. So finally, knowing this, we can write the matrix form of this gate, right? Because remember, if your Hilbert space is 4-dimensional, your operators, right? So this is your operator, right? this whole thing. Uh, this is your CNOT, right? And so it is something that is acting on the state of the combined two qubits on the composite system. This is very important to remember. You cannot disentangle the effect of the gate or either on psi or on phi. And so if I write this as a matrix, it takes the following form. Right? And it's very easy to read off what is happening. This is the diagonal part. The first two components are not affected, right? And this is the off diagonal part. This only swaps the last two components, right? So this is our CNOT gate, and I think at this point Rakshit probably has to leave. So I'll take your question, Rakshit.
No, it was like is the effect to change the coefficients, because if you scroll up a little bit, alpha 0 beta 1 became beta 0 alpha 1, right? If psi was 1.
Yeah.
So is the effect of psi on such a state only to exchange the coefficients?
That's right.
Okay.
That's right. That's all you wanted to ask?
Yeah.
Right. But again, remember that in these examples that I've given you, this psi is just a, so I've in these examples, I've not assumed that there is any entanglement between psi and phi, right? These are all product states. So when I'm saying psi is 0 and phi is so and so, so let me just say. So if I say that psi is 0 and phi is this, right? Then what is my total input state? My total input state is psi tensor phi, okay? How would I write that down? I'll write it like this: 0. Okay, and if you find it convenient to keep track of things, you can put a coefficient on the states to represent that you're talking about the first Hilbert space or the second Hilbert space, so the A or the B. Right? So if you take the tensor product of this, what does this become? This becomes 0, 0, 0 alpha and beta 0, 1. Right? And this is not an entangled state. This is a non-entangled state because I can write it as a product of the two states. But the key thing to remember is that psi need not be a product state in general, right? Because psi is an element of the combined Hilbert space. So for instance, my state psi, right? Now let me say my state psi is like this. Okay, so this is an entangled state. I can't write this as a product. Okay, and what is the effect of CNOT on this state? Right? So if you look at this in terms of components, you can write this as alpha 0, 0 beta, right? So this becomes alpha 0 beta 0 alpha 0, 0 plus beta 1, 0, like that. So the main thing is to again emphasize that these quantum gates, they act on the whole system, or if you have n qubits, you can have a gate. So in general, like you can have n qubits, and then you can have a gate which acts on 2 qubits here, another gate which acts on 2 qubits here, You could even have a gate which acts on all of these n qubits here, right? That is where the power of quantum mechanics is actually coming into play, right? The fact that you can work in this tensor product. Okay, so I'll stop here for now, for today. All right, and I'll leave you with the following exercise.
So like what will happen if our psi is also like a superposition state?
Well, so that's what we just worked out, right? I mean, if you look at a state like this, can you say that your psi is in the 0 state or the 1 state?
No.
No, no. In this case, you can, right? In this example, you can say that the A qubit is in a 0 state. This is a product state. This is a non-entangled. But this is an entangled state. Okay. Anyways, let me write down the exercise. Show that CNOT is an entangling gate, meaning that it takes product states and turns them into entangled states. But the thing is, the converse is also true. So you can also call it a disentangling gate if you wanted to, because it takes an entangled state and converts it to a product state. This is a product state over here. This I can write as alpha 0 plus beta 1 tensor 0. Okay, so I'm kind of like showing you the answer, but I mean, I want you to sit down and work this out yourself. Okay, questions?
So like for that the inversion to happen, we must have the control qubit as high, right?
The control qubit, so the control qubit should be, now again, this is what I'm trying to tell you, is that you need to move away from your classical intuition of and thinking of like things of things in terms of separate pieces, right? So you can, it's okay, of course, to say that the control qubit, if it's in the 1 state, then the target qubit is swapped. Okay, I mean, it's okay for the purposes of understanding. But the key point is that in general, the input state is some element of this larger tensor product space. So this kind of reasoning that if so and so qubit is in this state, that affects so and so qubit in that state, that only works at the level of the basis vectors. Okay, always please keep that in. I hope I answered your question. I'm not sure if I did or not. Any other questions?
So we call an entangled state when you can't write it as a tensor product, right? Or is
when you cannot write it as a product of as a tensor product state. But that does, so this is important to remember, that both the product state and entangled state, they are both elements of the tensor product space. Okay, so this tensor product space, this thing, it contains, so it is bigger than just the, if you take H1 and H2, H1 tensor H2 is bigger, right, than either H1 or H2. So it contains both the product states but it also contains these entangled states. And there are far more entangled states than there are product states.
Yes,
okay.
thank you. Yeah.
All right. Any other questions?
In the case of unitary gates, is it necessary to have 3 gates?
Is it necessary to have what?
3 gates, like.
Oh, you mean this construction that I showed you earlier?
Yes, sir.
Right. No. So this is just this is a very general statement. All it is saying is that any unitary matrix. Now, what is a unitary? We have a 2 by 2. A single qubit gate is a 2 by 2 unitary matrix, right?
Yes, sir.
And so that has 4 components, 4 complex numbers. Okay. But if you apply the unitarity condition, then the number of degrees of freedom. So how many degrees of freedom are there in 4 complex numbers? There are 8 degrees of freedom, right? Because each complex number has 2 components.
Yes, sir.
Right? But because of the unitarity condition, you can reduce that to a set of 4 real numbers like this, and then represent an arbitrary 2 by 2 unitary matrix as in this form. Okay. But this certainly doesn't mean that every time you have to generate a single qubit gate, you have to take a product of this. It doesn't mean that at all. Okay. That is not what it's saying.
While we are moving in the Bloch sphere, so there in the Bloch sphere, we have only 3 degrees of freedom.
3 degrees of freedom?
There is R, then there is phi, and then
R. But for the time being, I've kept R fixed.
Yes, so that's why
Okay.
I asked
So
this
I've
question.
kept R fixed. Yeah. So what happens is there's something called pure state and mixed states, and we'll look at them later. So the pure states correspond to the surface of the sphere, and when you go to the interior of the sphere, you are talking about mixed states. But we are not talking about that yet. Okay.
Yes, so that's why I asked that, since in the Bloch sphere we are considering R to be fixed, like R equals 1, then there is only theta and phi which can be changed.
Yeah.
And we are changing 4. We are working with 4 parameters. So how will we
extrapolate
to the Bloch sphere?
No. So there is a difference between specifying a state and specifying a gate. Okay. If you want to specify a state, you need to fix a point on the 2 sphere. Okay. For that, you only need 2 parameters. All right. Fine.
Yes, sir.
But a gate is a transformation of that state.
Okay, so got it. It's something like 2 cross 2.
Sure. I mean, whatever that means. I'm not sure what that means, but okay.
So like vectors, in case of vectors, if we are working on 2-dimensional vectors, so matrix will be 2 cross 2 dimensions. So it's similar in this case as well, right?
I mean, it's a matrix. It's a 4-dimensional. It's a 2 by 2 object. Yeah. So it has more degrees of freedom than just the state, obviously. Yeah. Yeah.
Yes, sir.
Okay. All right. So these are your exercises for today, by the way. That the first one is what was it? To work out what is the effect of this gate. Okay, plot the result of this on the Bloch sphere. Okay, and then the second exercise, well, which is sort of, I've already done it, but still, it's good if you do it yourself. Show that CNOT is an entangling gate. Okay. And we will talk about ways in which we can quantify entanglement in later classes. It turns out that given any state, there are certain quantities. So you can call it a function of that state. There are certain things that you can evaluate, and those give you a criteria for when your state is entangled and when it's not. So for that, we need to work with this density matrix picture. So then we'll talk about density matrices also at a later stage. Okay. All right, then I guess I'll see you all tomorrow then. All right. And again, if you have any other questions, please feel free to post them on Moodle or on Telegram, either directly or on the group. Okay. Okay. Bye bye.
Thank you, sir.
Thank you, sir.